Hey everybody, this is one last video we're going to do to wrap up thermodynamics here for you. And we're going to kind of cover one kind of more big topic, and then we're going to go through a couple of bits and pieces we think might be important to highlight. So Dr. Kim?
Yeah, one thing that many of the students are still kind of wondering about is the how do we use our common sense to predict the spontaneity of certain reactions? And for example, what about the burning of gas? Because many people think that because you have to actually ignite the gas itself to burn it, a lot of people think that why don't that be like non-spontaneous process? Dr. Crane, could you actually explain a little bit using the diagram that we actually learned?
All right, that's a really good question, and I'm going to turn on the little pointer here, and it's going to go to this point down here, this diagram that we've got down here. So if something is spontaneous, that doesn't mean that it just automatically happens. The phrase I've sometimes used in class is that you have to give it a little kick in the pants. Kind of imagine a ball at rest on top of a hill. If nothing happens to that ball, it's just going to stay at the top of that hill. But if somebody comes along and nudges it, then Mother Nature's going to take over and the ball's going to roll down the hill. So once that ball gets going, it spontaneously goes down the hill. So gas is kind of like the same thing. We all know that you have to light a match to get the gas to burn. So what you have to do with respect to this diagram here is, so here's our gas mixture, for example, okay, our gas and air mixture, and it's going to combust, and it's going to do that spontaneously, so it's going to end up lower than where it started. If we think of this axis as being free energy, it is negative, it is going down. But you can see that there's a barrier, there's a little energy hill to getting from reactants to products. Now, that barrier hill, it's going to have a term that when we get to kinetics, and what is it we call this guy again, Dr. Kim?
Activation energy.
The activation energy, that's right. So we're going to learn all about activation energy in kinetics. So when you think about the gas example, that match that you have to light provides that little bit of activation energy. Now my drawing here maybe isn't right to scale, but that activation energy is usually just a small little bump. But you light that match, and then Mommy Nature takes over, and sort of the metaphorical ball rolls downhill. So if something's spontaneous, it doesn't mean that it just automatically happens. Sometimes you have to kind of smack it a little bit to get it to go, but then it will go after that. So that's kind of one key idea to make sure we all understand as we wrap up on what really spontaneous means. Doesn't mean that it doesn't need a little push. Sometimes it will need that little push. So as we wrap up here, Dr. Kim, as you can see, we're all surrounded by all of these ideas that we've done here. So if you were to maybe pick out one or two ideas that you want the kids to really take home with you, which one of these great ideas that we've gone over would it be?
A lot of things that we actually have talked about, but the really key item that I would love for you to actually kind of internalize with you, especially I kind of joke around that this is the equation that I'm going to ask you when you walk down the auditorium with, at the graduation ceremony. It's right over here. Let me see whether I can circle it right here. Delta G is delta H minus T delta S.
Yeah, I sometimes call that the most important equation ever.
Exactly. The beauty of this equation is that gift free energy can be actually related to the enthalpy and the entropy of the system. So you don't really have to worry about what happens to the surrounding. Everything actually can be calculated and predicted using the information from the system. Now, you know the delta G number or the signs, then you can easily predict certain processes will be spontaneous or non-spontaneous or at equilibrium. And you guys all know at equilibrium, you cannot really tell whether it's going to go spontaneous or non-spontaneous. You're just at the right of the border, so delta G will be the zero.
Right. That is a great equation up there. That one is definitely one to remember. And like you said, all you have to know is the free energy change of the system. Whereas before, if you look down here, when we were talking about free energy and how it's connected to the entropy change of the universe, if you use entropy to try to assess spontaneity, you have to know about the entropy change of the system and of the surroundings before you can say if something's spontaneous or not. But by using free energy and the enthalpy and the entropy of just the system, you kind of cut the work in half, which is great. I guess if I were to pick something, I mean, they're all great ideas, but I do kind of like the equation over here, and this was highlighted in the second to last video, the one just before this, and that's called the Van Hoff equation. And one of the reasons why I do like this equation here is because, well, it's kind of useful if you know the equilibrium constant at one temperature, and you know the enthalpy of the reaction, you can predict the equilibrium constant at another reaction. And that's kind of helpful, especially if you're a chemical engineer who's working on a large-scale system or something like that. But the other reason I really like this equation is because the shape, the form of the equation. The natural log of two different parameters, or one parameter or two conditions, being correlated to some reciprocal differences in temperature. We're actually going to see that later on in the course in a couple of different contexts.
At least twice more.
At least twice more. So as great as that is, and of course it's great, as great as that is, and of course it's great, I like that one too, because I think it's going to be a theme that we're going to see before. So I think that's it, guys. I think we've taught you just about everything we know about thermodynamics. So keep this diagram in mind, because it's going to be kind of where we're going to start when we talk about kinetics, but that should just about wrap up thermodynamics. Take it easy.